All right, so we're going to continue today. We're going to continue our discussion of effective action, and I'll start with a summary of what we discussed in the previous lecture. So in the previous lecture, we discussed examples of two-loop diagrams in lambda phi 4 theory and saw that local counterterms cancel all divergences. In particular, we talked about this two bubble diagram that contributes to a propagator, and we saw that the counterterm that cancels it is this. Then we talked about this functor diagram that had a more involved integral, but we saw that to cancel that we needed two cross counterterms. One of them is this counterterm, the other one is an order lambda squared two loop corrections to the standard counterterm for the propagator, right? So that's del z order lambda squared. All right, so we also said that at least in we could just qualitatively discuss the divergences at higher loops. For example, these kind of bubbles that contribute at n loop to the propagator are order lambda to the power of n, they're n loop. Lambda, this is the cutoff, right? This is a momentum cutoff, and then there's a log to the power of n minus 1. Hopefully you recall where the log was coming from. It's just a simple dimension counting argument because these guys involve two propagators, right? So each of these loops contributes as log of lambda squared. The last one has only one propagator, so it contributes as lambda squared, right? Now in this example, we this is an n loop contribution and bubble contribution to the vertex, and this is lambda to the power of n plus 1 log of lambda squared to the power of n. All right, and the point was that we didn't prove it, but we quoted a theorem that formally ensures that the local counterterms that you start with will cancel all these counterterms to all orders in perturbation theory. Of course, you have to correct these guys at every order, but what matters is that you don't need to introduce new counterterms. It's just all it takes is a perturbative series expansion for these delta z, delta lambda, and lambda expansion, loop expansion. Good. Any questions?
So just to clarify,
Yeah.
like, so supposing like the fixed out there's order all the order term that's a order n.
Yeah.
When you got order n plus 1, any extra divergences that you get will all be able to be absorbed with the n plus 1 order two correction term.
Yeah, so you often package them as n plus 1 order n plus 1 you package it as things that you have already canceled at order n, and extra stuff that will be captured, for example, like terms like this. Yeah. That's goes like that's if you want to iteratively prove perturbation normalizability at all orders, that's what you do. Any other questions? All right. Then we switched gears and talked about the analogy between statistical field theory and effective action. And quantum field theory, sorry. We talked about the connection between statistical field theory and quantum field theory. And in statistical field theory, we have this thing called the Gibbs free energy that, yeah, that's what it's called. That is analogous to effective actions in quantum field theory. So here's like a comparison. On the left side, you have classical finite temperature fields, right? So this is finite temperature classical field theory. On the right side, you have quantum field theory, and this is a comparison. So for example, classical finite temperature fields, you can find them by doing some sort of coarse graining to the Ising mode, right? Coarse graining is when you take a bunch of spins and you replace magnetization as the average of the local, like the average of the value of the spin within that block, replace it with one block, right? The block. And of course, in the limit of blocking further and further, this becomes a continuous parameter. So you end up with a field, classical field. that classical field is the analog of phi of x mu, field in space-time in classical field theory, in QFT. The external source here is the magnetic field. You could have B of X that you could apply to align these magnets, right? And the analog of that in QFT is J of X. It's the source for the field phi. Here you have fluctuations, thermal fluctuations, and the size of these thermal fluctuations are controlled by temperature, 1 over beta, right? Here you have quantum fluctuations, and the size of quantum fluctuations are controlled by 1 over h bar. So the same way that in QFT you do perturbation theory in h bar, here you could do perturbation theory in beta or 1 over beta. We'll see that in a second. So the partition function on this side is d of b, right? Which is a path integral over magnetization. We saw that, right? E to minus beta h plus integral of b over m, right? The generating functional is the QFT analog of that, which is a path integral d of phi of j, e to minus s of phi plus j o. Here there's 1 over h bar. Small h bar means large phases. That's the origin of the stationary phase approximation or saddle point approximation. That corresponds to large beta. Large beta means small, low temperature. So the analog of small h bar expansion is low temperature expansion. Right? All right. The external magnetic field is like J, and magnetization is like the field. When dealing with partition functions, we define the Helmholtz free energy as minus log of ZB. Usually you put a beta here, right, to normalize that, to get rid of this stuff. I've just been a little bit sloppy with that. You can put that back in. That's the Helmholtz free energy, and the analog of that is in QFT is the generator of connected correlators, which is minus log of Z of J. If you had a 1 over beta or whatever here you would put the correct power of H1. Now, it's called Helmholtz free energy because its derivative with respect to B at fixed beta gives you M, the magnetization, right? The thermal expectation value of magnetization. And analogously here, taking derivative with respect to J gives us the 1-point function of the field phi, which is a classic, we call that phi classical, right? It's a field. It's a function. Good? Now, the analogy continues. We can do a Legendre transform, which to get a Gibbs free energy on the Statmec side. So that's taking FB and shifting it by MB to get G of M, right? We're trading the variable B for M, right? External source for the magnetization, right? And the analog of that here would be to take our Helmholtz free energy, the minus log of the partition function W of J, the generator functional of connected correlators, and shifting it by integral of J classical by Jx phi classical. This is called the effective action, right? This was the object of interest in the previous lecture, and this lecture, and the next lecture. The neat thing about this definition, the reason you do this is that it gives you the variation with respect to M gives you B of X, right? So it's like inverting the previous relation, right? So when we're doing the partition function, we're doing the partition function or Helmholtz free energy. The point was that we had a functional of B whose variation, whose saddle points or stationary condition will give you the magnetization, right? Now that's magnetization as points of external field. You could invert that relation and view the external field as a function of magnetization, and the corresponding function whose extremization will give you this relation is the Gibbs free energy, or in the case of QFT, it's the effective action. And today we'll see that this effective action is the generating functional for the 1PI diagrams. So let me tell you where we're going today with this. I'll first argue for this, then I'll go back and build a little bit, because I feel this switching to effective action was a little bit too quick. I'm gonna build on the motivation for why we're discussing effective actions and why it matters, and build on this connection a little bit more. I felt it was a little bit too quick last time. All right. So what we're set off to prove right now is we want to prove that this guy is the generating functional with respect to one PI diagrams. So let's start with the only relation that we know about. If you take the effective action and vary it with respect to phi classical, you're going to get the source, G of x. Good. That means that if I take a functional derivative of this guy with respect to jy, I'm going to get the Dirac delta function. Right? So I have del j of del effective action gamma del phi CL. Right? Now let's insert this variation. Right? So I'm just taking I'm taking del phi here and del phi here of z and integrating over z. That's just the identity operator, right? Okay. I do that so that on this side, I get a second derivative of the effective action. That's the point, right? I wanted to show that the second derivative, when I say that the effective action is the generating functional for one PI diagrams, it means that if I take two derivatives with respect to this, I should obtain the one PI 2-point function, right? That's what it means. All right. So I want to show that this is the one PI 2-point function. So that's why I took this out. Now I notice that phi CL was just derivative of del omega with respect to del jz, right? So I can write it this way. And now this expression just becomes a 2-point function J connected, because W is the generating functional for connected correlators. All right. Plugging that back in, I find that Dirac delta function is an integral over Z, the 2-point connected correlator multiplied by this object of interest. And said differently, what the second derivative effective action is a formal inverse of the 2-point function, connected 2-point function. It's a formal inverse of it. Good. And maybe I should pause here because I'm going to build on that, right? Is that clear? So I did this argument to tell you that the second derivative of effective action, the first derivative of effective action is just J. The second derivative of it formally looks like the inverse of the connected 2-point function. Yeah. Okay. Now let's take another derivative. So let's take 3-point function, connect the 3-point function. That is like another the del j of this guy, right? Now what I can do is I can take this as I can replace this guy with the second derivative of effective action minus 1, right? And insert again this thing in the middle, of course, with the integral in there. It's just the identity operator, right? Now, again, repeating the same logic as before, this bit gives me a 2-point function connected, integral over y. And now this, now this derivative is del phi of the inverse of the second derivative of gamma. That if you just as an operator, if you take the derivative of an inverse of an operator, that's inverse operator, derivative of the operator, inverse operator. That's just an operator relation. Is that familiar? It's an operator relation. If that's not familiar, work it out and see why. All right, so very good. So let's just rewrite what we wrote here. So the 3-point function connected is an integral of this third derivative. Right? I'm just putting everything together. This is the 2-point function connected, 2-point function connected, 2-point function connected, integral over y, the third derivative. This is the expression I have. Let's draw this diagrammatically. This is the 3-point function. It's connected, right? This is a connected 3-point function. This is equal to the third derivative of effective action multiplied by the connected 2-point functions. What is that? That is the 1pi vertex. The job, so what has happened is in going from the connected correlator to derivatives of effective action, for each insertion, we have taken out a propagator connected, or the connected part of propagator. That is what the 1pi vertex is. So you could view it as G3 divided by G2, G2, G2. Schematically. Now, repeating this procedure, you'll see, you can convince yourself that if you do a 4-point function, repeating just like basically all you're doing is that you're taking out, you're applying this thing. Del 5 classical y, Del 5 classical y, right? In between things. This is what you keep inserting. You're gonna write down the 4-point function connected as the fourth derivative of the effective action with 4 of these propagators, plus a whole bunch of other terms that this time the third derivative of effective action come out. It takes a little bit of work getting used to, but repeating this logic over and over again, you could derive that the nth derivative of the effective action is just the 1pi endpoint function. It was very quick, but I give you at least the algorithm for convincing yourself of this. And the basic idea is that the key intuition is that the second derivative of effective action is like the inverse of the connected to. That's the basic idea. That you repeat over and over again. Every time you take the derivative with respect to phi classical from gamma minus 1, more of these powers come out, and they correspond to more propagators that sit out here and will make your endpoint 1pi.
So what exactly was 1pi? One function? Like, is like that? I thought 1pi was a diagram which you cannot cut from that is you cannot partition into that's coming in.
Yeah.
The diagram that you showed, like 3 points.
Yeah, so for example, this is a 4-point function, right? That's not 1pi, whereas this one is.
Right, like, for example, if I look at the first figure,
Yeah, here,
yeah, it won't be have because
right, this bit, so you see, this whole diagram is not 1pi, because if I cut here,
yeah,
right? But the 1pi part is this part.
okay, so yeah, therefore this is the product.
Yeah, this is not 1pi. If this were 1pi, I would write in there. Right? This is the connected thing. Right? This is the connected thing that I've written. The connected thing I've written as the 1pi with connected 2-point function attached to every leg. So I guess your homework is to convince yourself an arbitrary endpoint function, in fact, written in this form, structurally is the 1pi. It takes some I'm in no way claiming that I explained this fully, but I'm pointing you towards how to start this. Right? Good. All right, so far what did we do? In analogy with StatMech, we argued for existence of something called effective action, whose variation with respect to, it's a function of something we call phi classical. Phi classical was a quantum 1-point function, whose variation was giving us the NPI, sorry, 1PI endpoint functions. It's a generating functional for the 1PI correlators. Good. All right. So let's build on the connection to StatMech a little bit more. Let me say it a little bit at a higher level. Let's just zoom out a little bit. The story is like this. Up until now, most of what we discussed in quantization of quantum field theory involves setups where we had A and A dagger as a like creation annihilation operator, AK and AK dagger, and canonical quantization as creating and annihilating particles, right? And the vacuum was defined as the state that was killed by all AKs, right? This leaves no room for 1-point functions, right? But in quantum field theory, so remember what the field is. The field, in analogy with StatMech, is the magnetization. So the setups where we have no 1-point functions, that's like no magnetization, right? But in StatMech, we often undergo these phase transitions. You end up with all sorts of, ferromagnetic phases where spins get aligned. The analog of that in quantum field theory are these solutions where phi is not zero. The expectation value. So phi classical is not zero. So what we're doing is that we're just taking our formalism of quantum field theory and taking one further step to generalize it to more interesting setups, right? So recall the Ising model. The Ising model had this like sum over nearest neighbor spins. There was a symmetry. There was a Z2 symmetry, SI going to minus SI, right? The Hamiltonian is invariant under this. But the ground state breaks the symmetry, at least 1D spin Ising model, right? It's either all up or it's twofold degenerate. Because the symmetry is present at the level of the theory, but the vacuum breaks it, that's called spontaneous symmetry. Right? It's the degeneracy of the vacuum. Now, in 1D, the moment you turn on beta, fine temperature, this spontaneous phase transition, phase symmetry breaking goes away, right? Remember that beta, non-zero beta is like the quantum analogy, right? That's like when you have quantum correction. So more interesting cases where beta is non-zero. Temperature is non-zero. In higher dimensions in 2D, if you take Ising model, there's a phase transition. At low, there's a critical temperature, there's a critical beta, and above that critical beta, below that critical temperature, there's spontaneous symmetry breaking and there's magnetization. Right? Which tells you that in quantum field theory might be in similar setups. So in QFT, the analogy, the setups where the 1-point function of the field is non-zero, we call that phi classical of X. And just argue for this, it's very easy. Take lambda phi 4 theory. We saw that in lambda phi 4 theory, when masses were positive, the 1-point function was zero. Right? But what if the masses are negative? So m squared is minus mu squared. Let's just analyze this Lagrangian classically, right? Minus half del mu. Okay, I have two mu's, but hopefully you understand this is space-time index. Plus half mu squared phi squared minus lambda phi 4. So first thing is, classically, this potential is kosher, it's fine, because it's bounded below. One of the things that you might worry, oh, you have a negative mass, so that might be instability. But because this thing is phi 4, it lifts, so if it's just like minus mu squared, this would be going down. So it would have like, it would be not be bounded below, but phi 4 will lift this and will give you this like double wall potential thing. Now, classically, there are two minima for this potential, and the minima are where phi is non-zero. It's plus minus square root 6 over lambda in the notation that I'm using, mu, which I'm going to call plus and minus v. Why is it plus minus v? Yes, but could you know that there would be two minima? Yeah, there's a symmetry. What's the symmetry? C2, yeah, phi going to minus phi. That remains unbroken. Sorry, yeah, I said incorrectly. It's broken, sorry.
How would we know that, for example, like, actually, no, ignore.
Yeah, I misspoke. It's broken, right? Because you're either an expectation value is v or minus v. If the potential, yeah, the potential is symmetric. However, the value of the field in the vacuum will not be. All right, good. So because the vacuum expectation value here is constant, well, let's just write phi of x as that constant plus sigma of x, right? Rewriting the Lagrangian in this language, there will be a constant piece to the Lagrangian, which is a constant, right? Remember, v is a constant, it's not a function. Lagrangian density, when I say Lagrangian. And then there's a piece that depends on space time. Now, if I'm doing a path integral over phi, this constant piece just comes out, right? So, and path integral variation of field phi is like variation of this shifted field sigma. So by change of variables, I can quantize, this is like quantization of this field up to this overall constant I've taken out. Good. All right, let's work out another classical example. There's a lesson to learn here. So sorry, let me pause here. Hopefully I already gave you some motivation for something like effective action. The starting point was that, oh, this lambda phi 4 theory that we're looking at that had m squared was a special case where we're ending up with no one-point functions for the field phi. Right? So that was special. There was something special about it. There's nothing sick about having a potential where the classical potential where the minima correspond to non-zero field phi. There are cases that we're going to study now, and that's where effective action becomes very important.
And so, in all of these cases, you always, what do you call it? You always transform variables to be like around the minimum point.
Yes. Yes. So recall when we said perturbation theory is asymptotic. It means that your perturbation theory is sensible, and at some point you start growing. That's often a sign that you're expanding the contribution of other minima become important. So let me say it a little bit differently. Let's say you have this potential and you start expanding around this point. You will see some funky behavior. You're expanding around the wrong vacuum. There's some sort of instability that shows itself as a bunch of terms growing. Yeah, let me not get too much into the details of it, but this expanding there could be many saddle points to your field theory, and every time you're doing perturbation theory, you pick a saddle point and do perturbation theory around that. At some point, this perturbation theory becomes so precise that the precision is comparable to the contribution of other saddles that you have to take into account to make your perturbation theory well defined. That is when the asymptoticness of perturbation theory kicks in. The contribution of other saddles has to be there to fix this. Right? That's the origin of the story. So the full non-perturbative theory, we will have to classify all the saddle points and do perturbation theory around all saddles, blah, 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 but that's not what we're doing in this course.
So is that why you said, you said that QAD is asymptotic? Is that the reason why?
QED is asymptotic. I said, no, sorry. Perturbation theory in quantum field theory in general, Feynman diagram perturbation theory in quantum field theory in general is asymptotic. Unless you're in very, very special setups.
And is that also because of the existence of the saddle points? and stuff?
Yeah, because we pick one manifestation, one simple way of describing is that you pick one saddle point, you start expanding around that. That was a little bit of an advanced comment, if that's not. All right, so there is a lesson to be learned here. That's going to be important for us, and it's going to be crucial. So I'm gonna go through one more example, which is hopefully familiar. So linear sigma model. This is a setup where you have a vector, real vector field, an n component real vector field phi A with symmetry On. Hopefully you remember this from part 1 of the course. The action for that, I'm gonna write the kinetic term, a mass term, which is gonna be phi A squared. Hopefully I don't need to explain this, right? This means that phi transpose phi, right? Trace, okay. Yeah. You know what I mean? And then this is the phi 4 term, which is phi transpose phi, trace of it squared. Why am I writing such particular terms? To make sure ON symmetry, orthogonal, is preserved, right? The action has ON symmetry. The same way that Z2 symmetry was a symmetry of the action in the previous case, phi going to minus phi. So I'm going to implement this continuous symmetry. The point I'm trying to make is the following. You saw when we studied continuous symmetries in classical field theory, there were conservation laws, there were no other currents, and there was so much going on. I'm going to look at spontaneous symmetry breaking of continuous symmetries to see if there's something special. And we'll see there's something very, very special about it. That's the point I'm going to try to make. Good? That's why I consider this model with a continuous symmetry, which is the ON model. And that's just, this is an orthogonal matrix. R transpose R is identity. This is a symmetry of the model. So if I look at this potential, so if there are, for example, if this is a O2 model, there's phi 1 and phi 2, right? The potential looks like this funky thing that I cannot draw, right? Well, Mexican hat, whatever it's called. All right, good. So already at this level, you see something funny. So your field is a vector, right? The second derivative of potential is a mass, right? V double prime of phi is a mass. If I view this vector in the polar coordinates, I can view the radial direction of it, which moves in this direction, and the potential in the radial direction has a mass, right? Because there's clearly a second derivative around there. Whereas the tangent, the perpendicular direction, the one that's just moves around the circle, the second derivative is 0, it's flat. That looks like a massless mode. The lesson we're going to learn is something is this. In summary, every time you break a continuous symmetry, you get a massless mode. For every continuous symmetry you break, you get a massless mode. That's called the Goldstone boson, Nabu-Goldstone. So we're going to see that, right? This is all classical, by the way. All right, so what does it mean to have spontaneous symmetry breaking? It means that you look at the vacuum of this Lagrangian, the minima of this Lagrangian, the minima of this potential, they could take, that's when there's any vector of length v, which is mu over square root lambda, would be a minimum of potential, right? That vector could be in this direction, could be in that direction, could be in that direction. They all have the lowest energy. So there's the vacuum, the vacua are manifold degenerate, which they're like for every, that you take a vacuum state. So in the case of 1D Ising model, you could take a vacuum all up, apply a Z2 symmetry, and you get another vacuum state. Here, the symmetry you apply is a continuous worth of, there's a continuous symmetry that will rotate you among these vacuum. All right. Good. So let's fix it. So here I was talking about radial direction and orthogonal direction. So it's like easy to, one way of thinking about simplifying life, real life is to say I'm gonna pick this to be in this direction. Now, radial means like phi n, and the perpendicular directions are like the orthogonal ones, right? So I'm gonna split my phi to v plus sigma of x. This is like the radial mode. And then these are the perpendicular ones. There's n minus one of them. Good. I take my action and write it in terms of these new shifted variables. What do I find? I find a kinetic term for these pi k modes, a kinetic term for this radial mode. There's a constant piece, of course. Then I find a mass term for the radial one, which has to do with the fact that this potential derivative is positive. There's a sigma cube term, right? There is an interaction term between these directions and the radial direction. There is a sigma 4 term, pi k2, sigma 2, pi 4, but no pi 2 term. That means that the pi fields are massless. Pi k's, there are n minus 1 of them, and they're all massless. ON symmetry is spontaneously broken to ON minus 1. All right, so here's a summary of it. There is something called the Goldstone theorem. It says every time, this is classical, this is fully classical. There's actually a quantum version of it that we're going to say in a minute. But Goldstone theorem says every time, so this is to be compared with, I could have taught this in part 1 of the course, classical field theory, right? When we're doing Noether cards. Every time you have a spontaneous breakdown of continuous symmetry, we have new massless scalar fields. Spontaneous means currents are conserved. You still have del mu j mu equals 0, right? As you expect from another current. But the ground state is not preserved under the action of symmetry transformation. The symmetry transformation changes the ground state, but not its energy. So ground state goes to a brand new ground state. So there's a subspace of ground states. These particles are called these massless particles that come from a spontaneous breaking of symmetry breaking are called Nambu-Goldstone boson. To every continuous symmetry continuous degree of freedom that we break, there exists one Goldstone boson. On has n times n minus 1 over 2 number of free variables, continuous variables. We break it to On minus 1, that has n minus 1 times n minus 2 over 2 continuous variables. So the number of continuous symmetries we've broken is n minus 1, and that's precisely the number of Nambu-Goldstone modes that we find, which is pi k, k running from 1 to n minus 1. Good?
This goes for any continuous symmetry, not necessarily over.
Yeah, I didn't prove the theorem, but I gave an example from ON, but the theorem applies fully.
Secondly, in the example that we consider,
Oops, what happened? Oh,
in the
Yeah.
example we consider, we said that the Lagrangian was conserved under symmetry. That the action is like preserved under symmetry transformation.
yes.
But in the theorem, we're placing the condition of the currents. Why exactly are we focusing on the currents here and not, for example, the action or something like that?
Well, it's the same thing. Once the action is invariant, another theorem, you just run this step by step and you prove that current is conserved. It's equivalent. Right? So it's equivalent.
So why should it always be a scalar field?
Oh, yeah, that's just a fact. It comes out of the theorem. It's always scalar.
Even if I do the same thing.
It's always scalar. Goldstone, Nambu-Goldstone particle. That's actually, well, hopefully I'll try to give you a homework problem. It's always scalar. Nambu-Goldstone is always scalar. Well, actually, Yeah, we'll work it out in the homework. All right, good. So I said this to say we get this nice, so this is a nice result, but this course is a course on quantum field theory. Are these mode gonna stay, once we introduce interactions, quantum interaction, right? Interactions and quantum corrections. We saw that actually here there are interactions, right? But it's just classical. Once we introduce quantum corrections, we saw that masses shift, right? There is mass renormalization. So the first question is that does this theorem survive quantum corrections? Do they remain massless quantum mechanically? Right? That's important. The answer is yes. They do not obtain any mass corrections. The masses are not normalized. So that's what we're going to discuss. Good. But this whole story is the Higgs mechanism. This is why our universe is massive and so on. There was a Nobel Prize that was given to these guys. Some people, Higgs and Nambu, those guys. There was a discussion at some point of, you've made it as a really good scientist if your name is used as a verb. That's very hard. Higgsing is a verb used in particle physics. There aren't many scientists whose names are used to form a verb. Anyway, some companies have made it. You can Google things, but. All right, so now I want to quantize it and prove that, well, we're going to study the quantization of spontaneous symmetry broken theories. All right. The point being, I want to show in this example that we're going to do renormalized perturbation theory really, really quick, as much as time allows, and show to you guys at least structurally. You have to do a lot of homework problems to figure these out, but structurally, there's no renormalization associated with these masses. All right. So, what was the first step of what was the actually? Yeah, let's ignore this. I think this is going to be confusing. What are we gonna do? We're gonna start with this action, right? And do renormalized perturbation theory. What was the first step of renormalized perturbation theory?
Wave function normalization.
Right. So you have to send phi A to Z phi A renormalized, but Z cannot have an A index. Why?
Keep it symmetric.
Yes, because otherwise it will break the symmetry, right? Renormalization is not supposed to break the symmetry, right? Good. All right, so then that will come with del Z. We put it in the metric. There are two, and remember what else would come out? There are two couplings here. One is mass, the other one is lambda. So there will be del lambda, del mu. There are three coefficients in renormalized perturbation theory. The theory that we have is a lot more complicated. So it is a question, can we capture all divergences? Can you cancel all divergences only with these three counterterms? So let's do renormalized perturbation theory. I think I wrote it somewhere. Whoops. All right. Okay, I guess I did not write it down. What you need to do is you plug in inside your action that v plus sigma of x, and then there was pi of k. So you end up with an action that looks like this, right? But then there will be the counter terms. So what I've written down here are the Feynman diagrams associated with it. So let's just first forget about the counter terms for now. Let's look at this term. This is just a propagator for the pi, this term, the propagator for the pi field. There's a label I and j that run from 1 to k, and I'm going to represent it using a single I. There's a propagator for the sigma term. I'm going to draw it this way. It has a mass 2 mu squared, so this is the propagator. This is massless. There is a vertex 3 three sigma vertex, here it is. There is a sigma pi k squared, right? Pi k sigma. There is the phi 4, a sigma 4, this is sigma 4, pi k 2 sigma 2, this, and then pi 4, which is this. Right? This is just Feynman diagram term by term for every single term in this. Now you can, it's already kind of confusing. You have a lot more vertices. Can you cancel all divergences using these three cross terms? Counter terms. See, keeps saying cross terms, counter terms. I don't know why I say cross terms. Now, as we said in renormalized perturbation theory, you multiply this by z. Here are your three counter terms, and the counter terms are treated as interactions, and they're here they are. They're Feynman diagrams. First thing to notice is that you're going to have a 1-point function, right? So part that was constant, the part of the dynamical action that was constant, okay, that's fine. You put it aside. But now you could actually introduce counter terms for it. So this is a 1-point function for the counter term, 1-point function counter term. This is something I'm going to do. I didn't do it here. You could open Peskin and go through it line by line, but you could also do it in your homework, and you will do it in your homework. There's this counter term. There is this counter term for the propagator, for sigma. This is the 1-point function of, this corresponds to a 1-point function of sigma, right? Why don't I have this counter term? Because that would mean that my VI's have 1-point functions, but VI's do not have, sorry, VI's, what do you call them? Pi i's have 1-point functions, but I said pi i's do not have 1-point functions. There is, I'm preserving ON minus 1, right? So there is no such a term, and that's the origin. That's the reason, right? So there is this counter term, which is the propagator for the pi fields. There's this counter term, blah, blah, blah. These are the counter terms you have. Again, remember that all you have is del lambda, del z, and del mu, and all of this. All right. What's the next step of renormalized perturbation theory? Renormalization conditions. So what are the renormalization conditions? Well, you want the 1 pi of sigma to be 0. Why? What is the 1-point function of phi? Is
So phi is zero.
v
Sorry.
plus this guy. So this is the requirement that we say the vacuum expectation value of the field phi is v, that thing, right? This is that condition. You want to preserve that in your Guanosis theory, right? That's just one condition. This is what is this? This is just, yeah, what is this? That's just a good old normalization, propagator normalization for this for sigma, right? Because this mass is fixed by the potential, right? What is this one? This is also the good old 4-point function, right? So this, the rest is just like family.
So what was the W? What's the W?
Sigma. So the massive mode, the massive, right? That's why I put p squared equal m squared, and m squared was fixed. Well, I forget 2 mu squared. That was m squared, right? Yep, 2 mu squared. Good. So what's the next step of a normalization? Say one loop. You want to do one loop renormalized perturbation theory. You'll have to take these one loop diagrams that you could draw and write down all the cross terms and see if all the divergences cancel. All right. The first thing that you want to worry about is the 1-point function for sigma at one loop. So at one loop for sigma, there is this diagram that contributes to 1 point function of sigma, and then there's this diagram. And then some corresponding counter. This should cancel. Now I haven't, you can open Peskin, look at the integrals, blah, 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 they will cancel. It's all nice. Then the propagator. There's this diagram that contributes at one loop to propagator, this diagram, this diagram, this diagram, the counter, and then all sorts of diagrams like this, but the cancellation of this is guaranteed if this cancels. Right? Because these are all like this guy attached to an external propagator, two external propagator. Well, there's a vertex in there. But right? So you see the structure of it, like there are always these sub-diagrams. So the cancellation of the sub-diagram divergences is crucial. Now, the key issue, the Goldstone theorem, relies on this guy, which was pi k remaining massless. If they're being massless, quantum corrections should not change the mass of it. That means that if you take this guy, this is a correction, quantum correction to the mass of pi. This is another quantum correction to the mass of pi, another one, and a counter term. Not only the counter term should cancel all the divergences, but it should cancel the final piece as well. It should be 0. Turns out it's 0. So this is, I absolutely recommend you read that page. There's a bunch of integrals and of Peskin. They go through this, Peskin-Schroeder, they go through this explicitly, and integrals can't order, they all cancel. The interpretation is that the mass shift of the field pi's is 0. This is a Nambu-Goldstone bosons. These Nambu-Goldstone bosons remain massless quantum mechanically at one loop. Turns out that they remain massless at all loops quantum mechanically, and something they could prove using effective actions. All right, any questions? I think I've been just going on this monologue. I should pause. Right. So what did we do? Any questions about what we discussed? Right. So to motivate a little bit more, the use of effective actions in comparing quantum field theory with statistical systems, statistical field theory, I said that we're talking about setups where there's non-zero 1-point functions or non-zero magnetization, right? An example that's very easy to arrange for in quantum mechanics and quantum field theory. That's where potential has non-unique vacuum, right? For example, if you have a symmetry and you spontaneously break it, meaning that there's a symmetry at the level of the Hamiltonian, but the vacua are degenerate. There are several field configurations that minimize the energy. We saw the Mexican hat version of it, and then we quoted the Goldstone theorem that says to every continuous symmetry you break spontaneously, there corresponds a massless mode, and that was sort of clear physically, right, what it is, because the potential has these flat directions. We call them flat directions, meaning that the second derivative is 0. So it can move around along those flat directions at no cost, energy cost, right? At least the second order. Then we took we saw that, well, if the 1-point function is just constant, right? It's just very easy. What you could just take it out of the path integral, redefine new variables, and what you're doing is you're just quantizing this like new variable, field variable that we call sigmas and pi's, right? You're expanding around this vacuum. And we did renormalized perturbation theory for this effective action corresponding to a linear sigma model, spontaneous broken symmetry, right? And the punchline, you go through these diagrams and you do your homework, you'll find that you set the correct renormalization conditions, you find that Nambu-Goldstone bosons remain massless quantum mechanically. I argue for it at one loop. You have to do the integrals to see. And you can look at the integral. I absolutely recommend you do it, or you will have to do it for your homework, but you will see that. All right. All right, are there any questions?
I know the saddles.
Classical saddles, yes. Yes, yeah.
Classical saddles.
No, saddles, yes. Classical.
So, like, the shouldn't be a problem, like, it's just.
Sorry, it shouldn't, well, what shouldn't be a problem?
Well, to be computing, like you said, there can be other studies which contribute at some groups.
Yes, yeah.
So, I mean, it's a hard finding out.
Yes. So, why is it hard? Well, let's just think about this a little bit. This is actually a very, very good question. What should you do? Saddles are what? They are solutions to classical equations of motion. What are classical equations of motion? They're differential equations. For a setup, for a system where it's mass, for free fields, what is this differential equation? It's the Klein-Gordon equation for scalar field, for instance, right? These are linear differential equations, right? So if you find two solutions, you add them, you get another solution. They form a vector space. You define an inner product on it. You could classify them, you could study them. There's like all sorts of things you could do. Now add an interaction term. You introduce nonlinearities. It's extremely hard. So you have a nonlinear PDE. Finding the solutions and classifying solutions to equations of motion is extremely hard because, first of all, there's no simple vector space structure anymore. If you find two solutions, you add them, it's no longer a solution. It's non-linear system, right? Classifying the set of all solutions to an interacting system is incredibly hard. These, besides free fields, where there are these like nice linearity results, there are in some very, very special quantum field theories, like integrable models, we happen to be in this happy situation where we tune the potential in a particular way. It turns out that there are some PDEs where we could classify all the solutions, and then those theories we can study non-perturbatively. There are all sorts of things we could do. But in general, it's just an extremely hard thing.
I only need to know the solution. So
You need to know. Sorry, okay. So you pick, you need to find one saddle point. You do perturbation theory around that saddle point. Of course, around that saddle point, perturbation theory at some point becomes so precise that the corrections need to be further corrected by the perturbations around other saddles. Right? So which means that you can't trust your answer unless you know about all other saddles.
which, like, so what I wanted to say was that I can get the others by just looking at the potential.
Yeah, by finding the solutions, all solutions to a nonlinear differential equation. If you take a course on differential PDEs, nonlinear PDEs, you'll learn it's a very hard thing. It's incredibly hard. So in some nice setups, like for example, of course, there are systems we're particularly interested in. For instance, gauge theories. Gauge theories are these when the differential equation is like it has a nicer structure, right? Then people study these solutions. They're called instantons, right? And you try to understand them, classify them, and that's been a route to some non-perturbative understanding of some gauge theories. Did I address the question?
Just for like section. So
Yeah.
when we say the vacuum, there's one true vacuum for EQT. Which
No. No, sorry. Wait. The term vacuum, okay, very good. The term vacuum is there's an abuse of the term vacuum here. There are several things that that are called vacuum, right? One is if you have a Hamiltonian, right, and you're looking at the lowest energy state of the vacuum. Now, this is what we've been looking at so far, and there could be several vacua, meaning that there might be several lowest energy states. right? This is one thing. The other thing is the following: you are doing a path integral, right, for your field phi. And this path integral could be, like it could be Boolean space. There's some sort of path integral over all functions, and there's saddles. In the saddle contribution to it, right? And small h bar expansion, that's like a saddle approximation, saddle point approximation. Every saddle point is sometimes called vacuum. So for instance, let me give you an analogy. In finite temperature field theory, what you're doing is that you're doing the path integral over the magnetization. What are the saddle points? The saddle points are minima of free energy. Minima of free energy at finite temperature, they're not vacuum, but they're the likeliest concentration. They're minima of free energy. If you want to think of them this way, we're talking about minima of these, like, yeah. All right. Any other questions? Yeah, other question?
I was kind of wondering, so like, we had that analogy with like thermal stuff where you have a phase transition when T is large, so is there something with like H bar was large? You like regain your centuries?
Oh, good. All right, very good. So you might have heard this. So in finite temperature, that's a beautiful question. In finite temperature physics, classical physics, we have phase transitions, right? This is when we take beta or some external fields and tune them. There are dials, we turn them, and at some point there's phase transition, undergo a phase transition. Something used to be some order parameter used to be 0, and all of a sudden it becomes non-zero at low enough temperatures. Usually high temperature restores all symmetries. What would be the analog of that here? We have a quantum field theory, right? H bar is not something you could tune. But in classical field theory, you could have phase transition in all sorts of, so you have e to minus beta h. You could have other sources. You could have like chemical potentials. You could undergo phase transition and detune chemical potentials. Here, what are the analog of chemical potentials? They're like these couplings. And in quantum mechanics, not even QFT necessarily, like quantum mechanics, a bunch of spin. You could undergo phase transitions as a function of couplings in vacuum. That has a name. You can probably guess what it's called. It's called quantum phase transitions. There's whole books on this. There's a book by Subir Sajdov that I would recommend, but the analogy is it holds precisely. Like even in finite quantum systems, you could have finite temperature phase transition as a function of these external fields, or it could have phase transition at 0 temperature as a function of couplings, and they're quantum. They're driven by so in one case, in finite temperature case, it's above the transition point, thermal fluctuations wash out any order, right? Here in the quantum case, above the transition or above the transition, right? Quantum fluctuations wash out. Thermal fluctuations wash them out. Quantum fluctuation wash them out. So, but that's a beautiful story. Any other questions? I'm worried about like starting this can of worms. Maybe it's a good point to summarize because actually let me tell you where we're going with this. I decided to have another lecture, an effective action. In the next lecture, I'm going to build a little bit more on this, and I'm going to give a very interesting. So far, sorry. Recall the set that we've been discussing in finite temperature. Always make a comparison with finite temperature. In finite temperature case, we applied B, external fields, right? That was a background field. That's why these effective action business is called background field methods, right? Now, you could wonder, So recall that we talked when we were talking about quantum field theory, right? I said that we cannot have 1 point function for a mu for gauge field. What was the reason? Lorentz invariance. I also said I cannot have a 1 point function for scalar field pi. What was my reason? Z2 symmetry. We saw that Z2 symmetry was spontaneously broken. It gave us some 1 point functions. So what goes on with gauge fields if you have background? What goes on in that case? That's going to be the topic of the next lecture. And with that, we're going to close this chapter of background gauge fields, and we're going to move on to non-perturbative renormalization. Yeah.
RG groups,
Sorry?
when I got discuss RG flow.
Yes. That's RG flow is the next, right? So there's a reason for that. Well, you'll see that, but what we do in normalization group flow is very similar to this effective action. Let me try to say the words now that we have a couple of minutes. What we did here was that we integrated the effect of the consequence of the effect of all quantum corrections and incorporated it into some sort of corrections to the action. Right? So we constructed this effective action whose variation gives you the 1 pi things. 1 pi have all sorts of quantum corrections in them, right? To all arbitrary order. That came from integrating all the quantum effects. Yeah, I'm worried about saying things that might be confusing, but yeah, you could try to integrate out the quantum effects due to some UV modes, right? So you have a cutoff at scale lambda. Now you say from this scale lambda and a scale a little bit lower the lambda. So in my integrals, I have to, when I do quantum field theory, normalized perturbation theory, I'll have to include all the quantum effects for every single mode below this lambda. Now, as you bring this lambda down, right? You could try to integrate out the effect of the quantum loops due to these particular modes and put them back in as a correction to your action for the lower energy modes. That's what we do in RG flow, right? We integrate out all the quantum effects due to running of UV high energy modes at the cost of shifting the action for low energy modes. So that's like philosophically the same. But there are another way of describing it. Yeah, so originally I wanted to do RG first, but then effective action is more actual here. All right, any other questions? Let's see. Do I want to say this? I think I do not want to say these. So let me summarize and then we'll stop. In summary, what did we go over? What did actually? Where did the lecture start? I have to remember. Oh yeah, we started by saying that effective action, this quick argument that effective action is the generating functional for the 1 pi endpoint functions. And the main logic that I want you guys to think about you should go through this derivation and do it for yourself. I might have typos on my slides as you've seen a lot before. The main idea is that this first derivative of effective action with respect to phi is J. The second derivative is the inverse, formally, is the inverse of the connected 2-point function. What was the inverse of the full 2-point function? That has a name. Propagator. Right, okay, so I'll stop bugging you. All right, so that's what it is. Now, what we built on this connection analogy between StatMech and QFT, right? And we said in StatMech, so our discussion of QFT so far has been limited to cases where the 0-point functions of the 1-point functions of phi are 0. That would because the action came with this Z2 symmetry, or in the case of ON model with an ON symmetry that was unbroken. Now it could be spontaneously broken, right? This happens in StatMech all the time. For instance, when there are phase transitions, right? Low temperature phase transitions in quantum mechanics also happens. And one simple example was this Mexican hat potential, right? We saw this phenomenon classically that every time you break a continuous symmetry, for every variable that's continuous, that corresponds to a continuous symmetry that you break, you get a massless scalar mode called Navier-Stokes boson. And we took the example of linear signal model. We quantized it in normalized perturbation theory, at least schematically at the level of diagrams. We wrote down all the counterterms. The first thing that was kind of magical was that we seem to have too few counterterms, but they cancel all the divergences. There's a beautiful couple of paragraphs in Pesky and Schroeder about that. You should definitely read that part. Then we saw that actually, I just said it in words that like we drew the diagrams and we claimed that not only we drew diagrams for the one loop corrections to the propagator of the pi fields, the Navier-Stokes bosons, and we said that not only the divergences cancel, but also the whole thing vanishes. That is required if the Navier-Stokes bosons remain massless at one loop, and it works out nicely. The claim is that it's true to all orders in perturbation theory, and there's a way to prove that using effective actions. Cheat sheet is Peskin, if it reads in Peskin, but we're gonna get there. Did I say anything else actually at this level? I don't think so. Right, so that's where we stop. Any last questions?
So is this just a very simple example where we only have to shift by a constant, right? And in general, you're not guaranteed to have something so simple to shift.
Very, very good question. So why a constant is a good guess? Does anyone have an idea?
What is the constant?
Sorry?
What do you know constant? What is the constant?
V. Why? It's not always the case. So you could cook up actions where that's not the case. That's not the vacuum. But why the vacuum is a good choice? Any thoughts? Think about the Hamiltonian. What does the Hamiltonian look like? If you have some wave like this, classically, how does it contribute to the Hamiltonian? It contributes like k squared, right? So the zero mode, at least classically, has the lowest amount of energy, and the moment you do any ripple, that increases the energy. So it's not a bad guess to start with. That's not to say that you cannot fine-tune Hamiltonians, that you end up with vacuum that are like Brett translation symmetry. So what that is breaking down of translation symmetry, right? So we preserve the translation symmetry. The breakdown of translation symmetry is a little bit funkier. People study it, but any other question? That was a great question. What's the name of it when we break translation symmetry in a system, many-body system? That has a name. Crystal. You could also spontaneously break time translation symmetry. That has a very, very fancy name, but it's a very simple phenomenon. They just feel you can understand it now very easily. It's called time crystal. It's a very fancy word for something simple. Spontaneous breakdown of time translation. What is the logic behind that? Why are we not seeing it? Because in the Hamiltonian, phi dot squared appears. right? So you don't expect those terms to, you expect minimum to correspond to phi dot equal to 0. However, you could cook up all sorts of models where that's not the case. All right. Any last questions? That was already the last question. So thank you so much, guys.